Today, we are tackling one of the biggest puzzles in modern physics. It's a tale of two particles that are, for all intents and purposes, identical twins, except one lives forever and the other vanishes in the blink of an eye. So that's the big question, right? How is it possible that two particles, which seem to be playing by the exact same rules, have such wildly different fates? Well, it turns out the answer doesn't just lie in some complex physics equation. To solve this, we actually have to completely rethink our idea of reality itself. All right, let's get into it. This whole mystery is known as the electron-muon paradox. So let's meet our two main characters. On one side, you've got the electron. You know it, you love it, it's stable, it's a core part of every atom. It's basically eternal. And on the other side, we have its heavier cousin, the muon. Now look at their stats. They have the exact same charge, the exact same spin. They're like two cars that came off the exact same assembly line. But here's the kicker. The electron sticks around forever, while the muon, it decays in just 2.2 times millionths of a second. Why? This is where things get really interesting. To crack this puzzle, we have to kind of zoom out, way out. We need to stop looking for a new particle or a new force, and instead challenge the very foundation of how we think about the universe. And that brings us to this really big foundational idea. What if reality isn't what we think it is? What if it's not a collection of separate little things, but is instead one single seamless fabric? Let's talk about this fabric of reality. The idea here is to picture the universe not as a big empty box with a bunch of tiny separate marbles, particles, rattling around inside it. Instead, imagine it's one single, unbroken, interconnected whole. In this view, there are no built-in edges or divisions. It's all just one thing. And this quote just hits the nail on the head. At the most fundamental level, there are no separate parts. The divisions we see all around us, the difference between me and the air I'm breathing, or a chair and the floor it's on, those aren't fundamental. They are concepts that we create. But hang on a second. If everything is just one big, seamless whole, how do we make sense of anything? How can we even talk about it? Well, that leads us to our next crucial point. The very act of knowing something is an act of separating it from everything else. You can kind of think about this in a few steps. First, you have the undivided whole, the fabric of reality itself. Then our perception comes in and makes the first cut. We see a tree, and we mentally separate it from the sky behind it. That's separation A. Then science gets even more precise. It creates formal models, separation B and C, drawing clean lines between, say, a particle we're studying, the instrument measuring it, and everything else. We are literally drawing lines on reality just so we can understand it. And what this really means is that our scientific theories aren't a perfect photograph of what's out there. They're more like a map, a really, really useful and predictive map for sure, but it's still a map we made by drawing borders and labels onto that seamless whole. It's a representation, not the territory itself. Okay, so let's tie this philosophy back to our original physics problem. This is where it all connects. What if particles aren't things in the fabric, but are actually shapes of the fabric? This is the huge leap, the core idea. What if particles aren't little marbles floating in space, but are actually just different configurations of space itself? Think of them as localized bumps or twists or even knots in this fundamental fabric of reality. So if we run with this idea, a whole new model emerges. A particle-specific geometry, its shape, is what gives it properties like charge and spin. But the scale of that shape, basically how much of the fabric you have to bunch up to make it, that determines its mass and its lifetime. And this leads to a really key insight. If two particles, like the electron and muon, have the same properties, it means they must have the same fundamental shape. They must be congruent. Okay, so we've laid all the groundwork. We have this new way of looking at reality and a new model for what a particle is. We are finally ready to solve the electron-muon paradox. And here it is. This is the solution in plain sight. The electron and the muon have congruent shapes. They're built from the same blueprint. That's why they have the same properties, why they're both leptons. But here is the critical difference. To make that shape for a muon, you need a much larger amount of the fabric of reality. And that one single difference in scale, it changes everything. This quote from the source material says it all. The muon isn't unstable because it's designed differently. It's unstable because of the sheer amount of stuff it takes to build it. It's the same design as the electron, just supersized, and that makes it fragile. You can think of it like building with Legos. A small, compact little car is super sturdy. You can drop it and it'll probably be fine. But if you try to build a massive, sprawling version of that same car using thousands of bricks, it becomes inherently wobbly and much more likely to fall apart. A larger, more energetic configuration in the fabric of reality is just plain harder to hold together. So we've solved the paradox. That's amazing. But the implications of thinking this way go way beyond just these two particles. Let's take a step back and think about what this really means for what we call knowledge. Because what's so powerful about this whole fabric of reality model is that it doesn't just neatly solve our little muon puzzle, it actually gives us a real physical intuition for one of the most famous and mysterious laws in all of quantum mechanics. You've probably heard of Heisenberg's uncertainty principle. One part of it basically says there's a trade-off between a particle's mass and its lifetime. The heavier it is, the shorter it tends to live. This model tells us why that is, physically. Let's just walk through the logic. A particle with more mass, like our friend the muon, is made from a larger volume of the reality fabric. That larger, more energetic shape is just inherently less stable. Remember the giant Lego car? And being less stable means it has a shorter lifetime. All of a sudden, this abstract rule from quantum mechanics has a simple geometric reason behind it. And this all brings us to a really profound final thought, something called epistemological humility. It's just a fancy way of saying we need to remember that our scientific theories, even the most powerful ones we have, are still just maps. They are incredible tools we've built by drawing lines on that seamless fabric, but they are not the fabric itself. They are not the territory. Which leaves us with a final, pretty mind-bending question to think about. If everything we know, all of our science, is based on the maps we've created by making these separations, just imagine what else might be hiding in the unseparated, unmapped fabric of reality, waiting to be seen.